Good day students. Today we will discuss the topic electric field intensity. To discuss this topic, we should have a prior idea about Coulomb's law. We know that by definition of Coulomb's law, F is equal to Q1 Q2 divided by 4 pi epsilon of R square AR vector, the product of two charges, and is inversely proportional to the square of the distance between the charges. Now, from the definition of Coulomb's law, we are going to define the definition of electric field intensity. The electric field intensity is defined as the ratio of force to the charge, or it is defined as force per unit charge. Therefore, E due to the point charge is defined by E is equal to Q divided by 4 pi epsilon R square of AR vector. E is a vector, so it has a unit of newtons per coulomb or volt per meter. Now we are going to find out E due to various charges. What are the various charges available? Point charge, line charge, surface charge, volume charge. We know by definition E due to the point charge is Q divided by 4 pi epsilon of R square of AR vector, and E due to the line charge is Q replaced by integral of rho L dl divided by 4 pi epsilon R square of AR vector, and E due to the surface charges Q replaced by double integral of rho S ds divided by 4 pi epsilon of R square AR vector, and E due to the volume charges Q replaced by triple integral of rho v dv. So these are the various possibilities of analyzing the concept of electric field intensity. In this topic, we will also learn the important university questions based on line charge and the surface charge. Okay, we'll have a clear idea about E due to charges distributed uniformly on a finite and infinite line. This is a repeated part B question. When I explain this diagram, please look on to the diagram carefully. Consider a line charge of length L meters. Now, the point P is located at a distance of h meter from the x-axis. From one end of the wire, it is located at a distance of L1 meters. The overall length of the wire is L meters. The point is located at L1 meters at a height of h meter from the x-axis. Now, there are infinitesimal small elements available on the wire. Let me consider one small element dx at a distance of x from left end of the wire, so that this portion is L1 minus x. Now, dE is a combination of dEx and dEy. So we are defining all these concepts theoretically to find E due to uniformly charged wire of length L meter, which has a charge density of either rho coulomb per meter square or rho L coulomb per meter square. It can be sometimes given in terms of lambda. So the angle made by the wire with respect to the point P is defined by alpha 1 and alpha 2. As you know that this is 180 degrees, the other angle is pi minus alpha 2. Next, the point P is at a distance of L1. So all these definitions we have seen. Now we are considering the element dx and we are moving towards the derivative part. Now, I need the analysis of this electric field intensity. By definition of electric field intensity of the line charge, we know that E is equal to integral rho L dl divided by 4 pi epsilon R square of AR vector. This is a known equation. This equation can otherwise be rewritten as dE equal to rho L dl divided by 4 pi epsilon R square of AR vector. In the place of rho L dl, I can also replace lambda dx. So the equation takes up the form of dE equal to lambda dx divided by 4 pi epsilon of R square of AR vector. Now, let dE be the field due to the charge element of lambda dx. So dE has components of dEx, dEy. In the diagram, I can say that dEx can be defined by dE cos theta, dEy can be defined by dE sin theta. First, our aim is to find Ex. So choose the equation dEx equal to dE cos theta. And now substitute the value of equation 3. dE already we have defined in this equation. So the equation is rewritten as, in the place of dE I have replaced lambda dx divided by 4 pi epsilon of r square ar vector into cos theta I have written as such. Now to find Ex, I have to integrate both sides. So upon integration, what is happening? Left hand side is becoming Ex equal to integral lambda of dx divided by 4 pi epsilon of r square of ar vector cos theta. Now, next our step is to find the value of dx separately, r separately. We can look on to the diagram. In this diagram, look on to the point of P, O, P dash. Now I can write two set of values from this diagram. If this angle is theta, this also we are considering to be equal to theta. I can write cos theta equal to sin theta equal to, from this triangle alone, consider P, O, P dash. Cos theta is defined by L1 minus x divided by r, whereas sin theta is opposite side divided by, so it is h by r. You know mathematically that cos theta divided by sin theta is equal to cot theta, which is equal to cos theta divided by sin theta equal to L1 minus x divided by r whole divided by h by r. Now, upon simplification of this equation, r and r are cancelled out, so I left out with cot theta equal to L1 minus x divided by h. So L1 minus x equal to h cot theta. Differentiate both sides. This is a constant, it becomes equal to 0, minus dx equal to, for cot theta it is minus cosecant square theta d theta. So the equation for dx is h cosecant square theta d theta. This is one value. Other value we have to find out for r. So by triangle we know that sin theta equal to h by r. So r becomes equal to h by sin theta, which is equal to h cosecant theta. Therefore, I am taking back the values of dx, r, I am substituting in the equation of Ex. Ex becomes equal to integral lambda, in the place of dx, h cosecant square theta d theta divided by 4 pi epsilon. R value is h cosecant theta, so h square cosecant square theta cos theta of Ax value. Because it is Ex, the component is Ax. Now cancel out the like terms. The equation is written in the form of lambda divided by 4 pi epsilon h integral, the limit is from alpha 1 to pi minus alpha 2 of cos theta. All terms are being simplified. Next step, Ex becomes equal to lambda divided by 4 pi epsilon of h integral of cos theta d theta, which is sin theta alpha 1 to pi minus alpha 2. So sine of upper limit minus lower limit. You know sin pi minus theta equal to sin theta. So equation takes the form of Ex equal to lambda divided by 4 pi epsilon of h into sin alpha 2 minus sin alpha 1 of Ax vector. Similarly, I can find out Ey component choosing the equation dEy equal to dE sin theta. Rest all procedure remains the same. Instead of previous equation integral cos theta, you have here sin theta. So again integral of sin minus cos, substitution of the limits results in Ey equal to lambda by 4 pi epsilon h cos of alpha 2 plus cos of alpha 1 of Ay vector. This is next step. Already we have seen that E is the summation of Ex plus Ey. First case, when alpha 1 equal to alpha 2, what happens? X component is an horizontal component. So x component of E is vanished. You are left out with E equal to Ey, which is lambda by 4 pi epsilon of h cos alpha 1 plus cos alpha 2 of Ay vector. Second case, when alpha 1 equal to alpha 2 equal to alpha, Ey becomes equal to, substitute alpha 1 and alpha 2 equal to alpha. So it becomes 2 cos alpha. Upon simplification, Ey equal to lambda divided by 2 pi epsilon of h cos alpha of Ay vector. Third case, when alpha equal to 0, Ey becomes equal to lambda divided by 2 pi epsilon of h cos 0 is 1. So lambda divided by 2 pi epsilon of Hay vector is equal to Ey, and the generalized equation of E due to the finite and infinite element is defined by E equal to, in the place of lambda I have replaced rho L, so it is 2 pi epsilon of R, A R vector is the value of E due to the line element.